Yes, so this presentation I gave almost, it's exactly the same on the CM meeting last week, but maybe it will sound a bit different this time. It's about an iterative ensemble smoother method that we use for solving the parameter estimation problems in oil-reservoir problems. And these methods have been used for a long time in state space, for state space solutions. But what we did here was to reformulate it in the ensemble subspace. And we found some nice mathematical properties of the method, and also it became very efficient. So the problems I'm interested in is the parameter estimation problem. We have some nonlinear model that maps a set of input parameters to predicted measurements, and then we have, of course, we observe these predicted measurements with some errors. And we can use a Bayesian formulation for this problem. So then we have a posterior PDF of X and the input parameters and the predicted measurements. So this is a joint PDF, conditional on the measurements. And this is proportional to a likelihood times a prior PDF for the parameters, and this is the model integration. And the main focus is on problems with a very high dimensional state vector and also vast data sets. So we are not looking at the standard simple inverse problems with just a few unknowns. And typically, the number of measurements is much less than the size of the state vector. So the problem itself, the inverse problem itself, is underdetermined, but it becomes well behaved by introducing a prior PDF for the parameters. And this is the problem we are basically solving in these whole applications. There is an analog problem which I called a data simulation, an indirect data simulation update. And suppose we have a numerical prediction model. We have a state variable, or it could be the ocean state or atmospheric state at a certain time ti. We run a model, nonlinear model forward in time and make a prediction. And then we have a measurement operator h that measures this prediction, and that generates the predicted measurements. And here, of course, if the model is perfect, like in this case, there are no model errors, we can insert m of xi here. And this also just becomes a nonlinear function of the inputs xi that maps to the predicted measurements. And then we can use, again, the same Bayesian formulation. So the problem is entirely analogous to the parameter estimation problem. But now we are solving for the initial conditions for a data simulation window. And it becomes similar to what you do in for example, 4D-var. And I call this the smoother update step in sequential data simulation. Okay. Of course, we don't have to solve for both x and y simultaneously, because if we know x, we can compute y. So then it's okay to integrate out y from this equation. And also, if the model is perfect, we can represent this transition density as a direct delta function. So we put this delta function in here, we integrate over y, and then we basically replace y with g of x in the likelihood. So this is really the inverse problem that we are solving. And now we can make assumptions about these, about the likelihood and about the prior PDF. And if we assume they are Gaussian, then we can say that maximizing this posterior PDF is the same as minimizing a cost function, quadratic cost function of this form. Okay, we are working with ensemble methods. And for example, in 4D-var, you would minimize this cost function. If we are working with ensemble methods, then you can show that you approximately sample this posterior PDF by minimizing an ensemble of cost functions, where we now have this XJF is a sample of the prior with a certain covariance, and here we have similar sample measurements with this covariance. So by solving, and these problems are not completely independent of each other, so you can solve for each J again and again and generate as many samples as you like. And we can also show that if the model is linear, then this exactly samples the posterior. If the model is nonlinear, it's an approximate sampling. Okay, if we suppose now we start with this ensemble of cost functions, and okay, so the typical way of solving this, or the traditional way of solving it, is to compute the gradient of the cost function and then use some kind of iterative method to minimize it. And that would typically be like you do in 4D-var. In the ensemble approach, you will again compute the gradient and you will minimize in the state space. And what you can show is that the solution of the posterior ensemble is entirely contained in the initial ensemble and initial ensemble space. So what we did here is to search for a solution in the ensemble space. We write that each realization, the updated realization, is equal to the prior realization plus a linear combination of ensemble anomalies. So this relates to what Hunt did in deriving his 4D-var scheme. And A is just ensemble anomalies, so it's the original ensemble with the mean subtracted. And if we insert this solution into the cost function, we get a new set of cost functions where we have eliminated all references to the full state vector and also the full state covariance matrix. That actually becomes a diagonal here, and the dimension of the problem is now the ensemble size instead of the state size. And this becomes, well, it should in principle become a much easier problem to solve. What we can do now is to compute the gradient of this cost function, set it to 0 and minimize. The gradient looks just like this. You have the tangent linear operator of the model here. This is the initial ensemble again. And you can also compute the Hessian or approximate Hessian and use this in a Gauss-Newton method. And if we do that, and with some manipulation, we end up with this following equation as an iteration of the W's. So for each realization, again, each of these equations are completely independent of each other, but we now have an iterative scheme for each realization. And we have to evaluate this particular term. And that we could do using an adjoint, and then this would correspond to whatever, like ensemble 4D-var. But in the methods or the models we are using for all of our petroleum applications, we don't have access to the adjoint. We don't even have full access to the equations they are solving. What we have is a model that takes some inputs and generates some outputs. So we need to do something with this term, defined like here. And this is really the crux of the method. So we make some additional approximations. We say that we replace this exact model sensitivity or tangent linear operator with an averaged sensitivity of the model. And we define it just GI. This. So we have not really said what it is yet. But what we can do, since we are working with an ensemble method, then we can approximate this GI with an ensemble representation through a linear regression. So that means we are using a kind of least squares best fit representation of G averaged over the ensemble. And Y is here the predicted measurement with the mean subtracted. And A plus is the pseudo inverse of the ensemble anomalies. So what we have is we start with this expression. We approximate it with this simplified or expression where we use the averaged sensitivity, and we use the linear regression definition for the G. So it looks like this. And I think this is where the problem starts mathematically, because it's not easy to say anything about this term or So, and this term is also still the dimension of the state space. So it's a big matrix. However, what we could find or show is that we can represent these initial ensemble anomalies by this deconditioning, or where you take the ensemble anomalies at time I and then propagate it backwards to the initial time. So basically we have A is equal to AI times omega minus 1. And this omega matrix is just identity plus the weights with the mean subtracted again. And we can show that this is full rank in most problems. And this expression is quite nice because it's just a projection that subtracts the mean from this y. And since y already has the mean subtracted, it doesn't do anything. So we can just cross it out. And that's true for all cases when the state size or state dimension is larger than the ensemble size minus 1. So we just define this expression to be, I call it S. And our final equation for the updates of the coefficients W, and now it's for the whole ensemble here, looks like this. And here we recognize the Kalman gain. And this is just the innovation term, and with this correction that takes into account that it's the prior term in the iterations. And typically to solve this, what people do is to use Woodbury. So you rewrite it like this, and then you assume that the error covariance matrix for the measurements is a diagonal matrix. And that this simplifies a lot because this becomes an inner product now. So we have a matrix here, which is the dimension, the ensemble size. So if you have 100 realization, this is a 100 by 100 matrix. So it's easy to solve. So this is the main motivation for using a diagonal error covariance matrix in most of these schemes. What we are doing is to use a different algorithm, actually quite an old algorithm, where we replace the measurement error covariance matrix with an ensemble. So we represent this using an ensemble of perturbations. So we write it like this, and then we project these perturbations onto the ensemble subspace, like this. And with some manipulation, we get a very simple equation in the end, where what we invert is a diagonal matrix, the size of the ensemble, and the main computation is the SPD of this S matrix, and that's linear in the number of measurements. So in a way, we have an inversion now that takes into account cross correlations between measurement errors, and which we can compute linearly in the number of measurements. So in the end, we have the whole algorithm. So we have the inputs, it's just the initial ensemble of, or the prior model ensemble. We have the perturbed measurements, and then we create measurement perturbations. We integrate the model forward in time in this loop. We construct these matrices, we solve these linear systems. We set up the right-hand side, or the innovation part here, and we compute this iteration. We have a transition matrix that depends on the W, and we update the ensemble. And then that's input here again, and we just repeat. And all computations in this algorithm is no order linear in the number of measurements and linear in the state size. And this is just one example. It's from a paper that just appeared. Here I use an ensemble size of 100. And another thing we're doing is that since we approximate the error covariance matrix for the measurements, we decide to use more realizations than the normal ensemble size to reduce sampling errors. And typically, here I use just 10 times the ensemble size. And that basically eliminates any sampling errors you introduce by this approximation. And I used 200 measurements, so I have twice as many measurements as ensemble members. And I use correlated errors, so you can see all the measurements are they are correlated with each other, so they follow more or less the same line. And they are measurements of the truth, which is this line here. And then the state size is 1000. And what I show here are two solutions. One where I use the full error covariance matrix, and one where I use the representation by ensemble perturbations. And you can see they are essentially on top of each other. And also for the estimated variance, this is the initial variance, and this is the estimated variance in this case. So again, here the two cases are on top of each other. So this is basically a verification that we can solve the problem with correlated measurement errors, and also that this representation using the ensemble, the measurement perturbations, is consistent. And then I will show some examples from a reservoir case. In this case, we have 28,000 model parameters. It's the full three-dimensional porosity field of the model, and some additional scalar parameters like fault multipliers. We have the 453 measured production rates, and we have an ensemble size of 100 again. And this is just showing the convergence of the different cost functions, because I have an ensemble of cost functions, and these are the initial values, and then after about 4, 5, 6 iterations, they have all converged. The thick line with the yellow dots is the average cost function. So in 4 to 5, 6 iterations, we have a solution. This is an example of two fault multipliers. We have the initial multipliers here, and there are 3 cases here now where I'm using different variants of these inversion schemes, and they all give very similar results. And I also show 2 examples here. These are 2 different production wells. So I have the initial ensemble in blue, and then the red is the posterior ensemble, where I am rerunning the model using the updated parameters. And this is using a full covariance matrix, and this is using the perturbed one. And again, you can see that it's almost impossible to see any difference in the estimates, the red curves. And we get predictions that are quite consistent with observed production. Okay, so this method is now operational in some softwares, and is used in like Equinor, the Norwegian oil company, to match their or fit their models to data in all the assets. It approximately samples the posterior PDF for nonlinear problems, but of course, if it's too nonlinear with multi-model behavior, it will not work. We avoid using model adjoints by using this ensemble average model sensitivity. It's a computationally very efficient formulation and implementation, and it can take into account the correlated measurement errors. So there's no inversion and factorization of large matrices. In addition, we can use local analysis. There's a paper here that describes that. Also, I did some work where we include additional model errors in the system, and we also can use that. And for the case with additional forcing errors or controls, there's a new paper that just came out that discusses it. And yeah, there's a list of publications here, and I will send you the presentation so you can access these links easily. Yeah, so I think I'll spend my time there.
Okay, Geir, thanks a lot for a very interesting talk. We have a question from Peter Jan van Leeuwen. So he says, the ensemble mean will converge to the maximum a posteriori estimator. But can you say more about the ensemble, what the ensemble converges to? And then a postscriptum saying, by the way, if you have the adjoint, multiple modes can be found, correct?
Yeah. I don't know where to start. If you have the adjoint, you should use the adjoint, and then you have a much better, you will have a better solution. You will be able to recover multiple local minima and multimodal posteriors. That's okay. What the method convergence do is not clear. Because it's an approximation. Again, you could compare it, and we did actually compare it to particle flow implementations for simple cases, like scalar cases, and then we see that while particle flow will converge to the exact posterior PDF, then here you get something that's a little bit off. But again, this is not a method that's supposed to solve the full nonlinear problem. It's a method that gives you a reasonable and an acceptable solution in very many industrial applications and high-dimensional problems and in a very efficient way. So.
Thank you. The second question is from Xuan Wang, and she says, does the convergence rate depend on the ratio of ensemble size and dimension of the state?
The dimension of the state doesn't matter here. You can multiply it with 10 and still have the same coefficients in W. And you're solving everything you're solving for this linear combination. The only impact of the ensemble state, well, of course, if you completely change your model, you have a different nonlinear dynamics. But I would think the convergence rate might depend on the ensemble size, because you get a more noisy sensitivity matrix with small ensemble sizes.
Thank you.